Hello, good morning, guys. Glad to see you here. Today, I will talk about the software load balancing for cloud deployment. My name is Hongjun. I'm working on DPDK and FIDO at Intel. Now I'm the SweetCom project leader and the service function project leader. First of all, this is a joint effort from Intel and Cisco. So I will need to thank you all the guys. Ricky, Steve from Intel, Pierre Jerome from Cisco, and Ping and Jeff Shaw from Intel. They have given great contribution to this project and the slides. Okay, since this topic has 50 minutes, so I will talk about the key components for this project. The first one is why we're choosing FIDO. The second one is a three-level load balancing solution, and we will explain the details for each component, and then we will talk about two-level load balancing solution, and then final way. So, first of all, I will do a survey. How many guys know about FIDO and VPP? Could you please raise your hand? Oh, okay, thank you. Okay, you know, FIDO is a mature ecosystem, and there are lots of sub-projects in this under FIDO umbrella. So I will talk about this from the bottom to the top briefly. On the bottom, it's the packaging system for all of different operating systems, such as Ubuntu, CentOS, Debian, and lots of that. And on the network I/O layer, it's the DPDK power driver, and to accelerate the interface performance. And on the green packet processing side, there are many sub-projects. The core is VPP, which means vector processing, vector packaging processing. So it handles the thread thread handling and the memory management and the IPv4, IPv6, and layer 2, layer 3 protocols. And then there are lots of sub-projects based on the VPP, such as the DMM, which was proposed by Huawei, which can cooperate different host stacks, such as the Linux TCP kernels, and the VPP host stack, and also the F stack from Tencent. And the P4VPP is initiated by Stanford University, which handles the P4 language and translates the P4 language to the VPP, and also the Go VPP. You know, VPP can provide different APIs for different languages, such as C language, C++, Python, Go, Luna, and Java, lots of languages. And on the management agent, there are 4 different sub-projects. The first one is the Honeycomb project, which is used to integrate with the OpenStack and the OpenDaylight and the VPP. And the networking VPP is used to integrate the OpenStack and the VPP. And the Continue VPP is used to integrate the Kubernetes, Legato, and the VPP for the cloud deployment. And also, the first use case for the ONAP, the residential CPE use case, is also developed based on VPP. So also, the system is used to integrate different function tests, performance tests. You know, VPP can publish the performance test for each release. So, and the TREX is a packet generator based on DPDK. Okay, this is the option 1. It's a 3-level load balancing solution for cloud. You know, there are 3 key components for this. One is the route, the second one is load balancing, and the third one is the service proxy. You know, the route, load balancing, and the service proxy now could be supported by based on the VPP and the DPDK. And also, it can support the IPv4 and the IPv6. So for this solution, it runs as a typical Kubernetes cloud networking solution. Okay, we will explain the 3 components in details. The first one is the router, is a VPP. There are 2 ways to integrate the routing daemon and the VPP. One is you can integrate the routing daemon, such as board or FR, with the VPP directly. But there are some code changes for the routing daemon. So we proposed another solution, which is the injecting mode, which means you can run your board or FR on the Linux kernel, and that doesn't any change for the code. So we play the tricky way for you to mirror the routing tables into the VPP table. So actually, this is a diagram. There are many steps for this. First one, you need to create one tab for each interface, physical interface. Then you will cross-connect the physical interface with each tab interface. Then when you receive the protocol package, and the VPP router plugin will inject these protocols to the tab interface, and the board will receive the protocol package from this tab interface, and it will manipulate the protocol package. And then, if they need to configure the Linux kernel tables, they will use the netlink to interact with the Linux kernel stack. When the board configures the Linux kernel stack, the routing netlink plugin will listen for the netlink messages, such as the address, link, neighborhood, and the routing tables, and then mirror the configuration to the VPP forwarding information database. So currently, for this plugin, we can support IPv4 and IPv6 and MPLS. So this is the load balancing implementation. Actually, there are 3 components for this. One is the load balancing, and the second one is the connection track, and also the tunneling encapsulation. For this load balancing, it can distribute traffic among different Kubernetes nodes, and then for the load balancing is based on the consistent hash, which is similar like the Google maglev. So it ensures everything, the flow to all the packages belonging to a flow to a same Kubernetes node. Currently, we can support the layer 7, layer 3, and layer 4 load balancing, and can support 2 different encapsulation types, such as the GRE and IP-IP tunnel. So actually, for this, the good news is that for this, the load balancing has been implicated with the OpenStack, work as a load balancer as a service by Yahoo Japan and Intel, and it can publish at the Tokyo University last month. For the service proxy, actually, it shares some code between the load balancing, but there are some specific components such as DNAT and SNAT. So for this service proxy, it can distribute traffic between different ports. And we currently can support 2 initial high-performance interfaces, such as the vhost user and the VTIO, and also the member if. Now we can support 3 different service types, which is required by the Kubernetes. One is the cluster IP and port. The second one is node IP and node port. The third one is external load balancer. So for DNAT, it can translate the service IP to the port IP, and SNAT does translate the port IP to the service IP. Okay, this is the data flow for the solution 1. When the VPP router receives the package, it will enable the internal load balancing, which ensures all the packets belonging to a flow to send to a same load balancer. And then when the VPP load balancing receives the packets, it will distribute traffic and encapsulate the package through the GIE tunnel or IPIP tunnel. A specific payload will be sent to the same Kubernetes nodes. On the Kubernetes nodes, it will perform the node-level load balancing. So it will remove the GIE tunnel and then go through the service proxy load balancing algorithm and perform the destination net, and also distribute traffic to the selected ports. For the return package, it will also pass through the service proxy. In this case, the port IP are not visible to VPP load balancer. Okay, this is the second solution. It's the two-level load balancing solution, which means here we also run the router load balancing and the virtual router on the Kubernetes node. Each load balancer and Kubernetes node runs the BGP protocols. So load balancers and each Kubernetes nodes, they can do the full mesh. As a result, load balancer and each Kubernetes nodes know the port IP address for each node. So for the data flow, we can say when the router receives packets, it also does the internal load balancing feature to make sure each flows to same to the same VPP load balancer. Then VPP load balancing receive packets, it will select ports directly as per the service IP and encapsulate packets through the IPIP tunnel or GIE tunnel. And then on the Kubernetes node, the router will just forward IPIP traffic to the selected ports. And on each port, it will remove the IP tunnel and manipulate the packets and also swap the source IP address and the destination IP address. Then the return packets will directly sent to the clients. So which means the direct server return. Okay, this is the key takeaways. We provide a user space solution to enable high-performance cloud-native networking. So we also provide a three-level load balancing solution for typical Kubernetes usage. So we will explain the router load balancing and the service proxy based on VPP and DPDK. And we also provide two-level load balancing solutions for direct server return. Thank you. That's all from me. Any questions on this? Okay, thank you, guys. Thank you.
Thank you.